In this series of videos, I'm designing a Z80 based computer system. In the previous video in this series, I showed these two circuits separately. The circuit on the right is a PS2 interface. It converts the serial data from a PS2 keyboard into a form that the Z80 can read in. So it also generates an interrupt output because the keyboard will be driven through an interrupt system. So I also needed the interrupt controller, and that's the circuit on the left, which I also demonstrated. As you can see, I've now brought them both together, and I'll just briefly demonstrate this before we move on to hooking this up to the Z80 itself. So the LEDs on the left are the data bus. That's effectively the data bus that will be connected directly to the Z80. And of course these two circuits both need to output data. The one on the left, the interrupt controller, needs to output the vectors for the device that's generating the interrupt, and the circuit on the right, the PS2 interface, needs to of course output the PS2 data byte. But they can't do it at the same time, and also they must only do that when the Z80 tells them to. So this is powered up at the moment. It's a fairly simple arrangement, as I demonstrated, and just going to clarify exactly how this works. So the PS2 part of the system has a single control line, and this goes low whenever the Z80 wants to read the data from the buffer that effectively converts the data from the PS2 keyboard. This blue lead is the interrupt output, so it's got one control input that does two things. It resets the circuit to make it ready for the next data byte from the keyboard, and it also outputs the correct value, or the data value, onto the data bus, and those two actions are combined into one control line. So when this line goes low, it resets and outputs the data, and the interrupt output from that circuit is currently connected to our second interrupt input. So the blue line is the interrupt 1, which goes to our interrupt circuit, the red is the interrupt 0, and the yellow is interrupt 2. So we can have up to 8 interrupts with this particular arrangement. So I'll just quickly demonstrate this working, and then we'll hook it up to the Z80 itself, and we'll need to then write some software in order for this to actually work. So when we press the key on the keyboard, the circuit on the right will effectively convert the incoming serial data from the keyboard into a parallel form that can be read by the Z80, and it will also generate an interrupt. So the output for the interrupt line is shown on this LED at the bottom right here. So if I press a key on the keyboard, the LED comes on, that generates an interrupt, and we can see that the interrupt on the left has been triggered. So this LED at the top left here is effectively the interrupt in that goes to the Z80. That will trigger the Z80 to generate the interrupt. And these two jumpers here, one would normally come from the in-out request line of the Z80, and the other one would come from the M1 line, so that the special M1 cycle that the Z80 generates in response to the interrupt will cause these two lines to go low. So if I take these both low, what we'll see is the interrupt vector for the keyboard, which is interrupt vector 1, will appear on the data bus, and this will occur when the Z80 is trying to read in the vector. So the Z80 will then read in the vector, it will jump to the interrupt handler, the interrupt handler will then read the data from the keyboard interface, and during that process this line will go low, and as you can see, that clears the interrupt. It also resets this circuit, but it also allows the circuit to output the keystroke value onto the data bus. So we'll do another one, we'll press another key, that will generate another interrupt, the Z80 would read the vector. It will then read the data byte from the keyboard. That resets the circuit. It will then accept the next, and so on, and it can do that obviously very quickly. If it's a different interrupt that's thrown, so in this case we'll throw interrupt 0, the Z80 will generate its special M1 cycle, and we can see this time we're getting interrupt vector 0 appearing on the data bus. The Z80 interrupt handler would of course clear the source of the interrupt, and if we try one more, we'll go to interrupt number 2. The Z80 will then ask for the vector, which will be put onto the data bus, and this time we can see we're getting vector 2. Okay, so what happens if there's more than one interrupt at the same time? So to simulate that, what we'll do is we'll simulate that the second level interrupt has been thrown, and as the Z80 starts to process this, someone decides to press a key on the keyboard. Notice that the LED on the PS2 interface came on as well. So now there are two interrupts pending, but the one that takes priority is of course the higher priority interrupt, which is interrupt number 2. So when the Z80 generates its M1 cycle, notice that the interrupt vector that's put onto the data bus is for interrupt 2. So once it's dealt with that, the handler will get rid of whatever caused the interrupt, but notice that the interrupt LED is still on, and so is the LED on the PS2 interface. So this time when the Z80 generates the M1 cycle, notice that the vector is now different. It's the vector for interrupt 1, which is what we have our keyboard connected to. So in this case, when the Z80 handler reads the data from the keyboard, it will cause this to reset. That clears the interrupt. We also get the data on the data bus for the keyboard, and then all the interrupts have been dealt with. Now on the other hand, if the first interrupt is a lower priority interrupt than the keyboard, then the interrupt for interrupt 0 is thrown, the interrupt LED comes on, that will trigger the Z80 into its mode 2 interrupt handling, and let's again say at this point someone happens to press a key on the keyboard. Again we can see that the LED on the PS2 interface has been activated, but this time, by the time the Z80 gets to its M1 cycle, notice that the vector is actually for the keyboard, not for the interrupt that was thrown first, and that's because the keyboard is priority 1 and this one is priority 0. So the Z80 will go ahead, it will process the keyboard. We've still got the interrupt for the priority 0 interrupt. That will then cause the Z80 to read the vector for that particular interrupt. It will jump to the handler, that will clear the interrupt, and again all the interrupts have been handled. So this way, this mechanism allows us to handle multiple interrupts. This time we've got 3 interrupts pending. The first one is the highest priority for 2. The next one would be for the keyboard, and then the final one, if we clear this, the final one would be for interrupt 0. So as you can see, the circuit works very well. It's going to allow us to completely eliminate the need for any of our hardware devices to need to deal with putting vectors onto the data bus. It allows for very easy control of our peripheral circuits, in this case just a single line, does everything we need for the interface, doesn't occupy any additional time from the Z80, and also if someone wants to write their own operating system for this particular computer, they don't have to concern themselves with either messing around trying to poll the different devices to see which one generated the interrupt, and also they don't need to worry about the timing or repeated interrupts that would be required to interface to the PS2 keyboard. So this entire mechanism is now ready to attach to our Z80. The only thing we need to make it work is to attach the data bus, the in-out request, the M1, and then the interrupt out. So this line where we currently have the red LED attached would normally go to the interrupt in pin of the Z80. We then need a read line for our PS2 interface, and that's it. We don't need any other connections to this for this entire system to work. We will need some software to make this work, of course, but it will be fairly minimal. I say minimal, it is fairly complex, relatively speaking, to set up mode 2 interrupts. It's not particularly difficult, it's just a bit complex because you need to work out what addresses you wish to use. But once you've got it set up, once you've done it a few times, it's very straightforward. But ultimately it's actually easier, at least in my opinion, than say mode 0 or mode 1. And there are other issues as well with using other interrupt modes such as mode 1. The mode 1 interrupt, when it's thrown, will jump to a specific address, and it's an address that's low in the RAM space. And the problem that you have is if you have a multiple bank system, then you need to allow the interrupt controller to switch banks whenever an interrupt is thrown, otherwise it can't access the interrupt handler vector, and that in itself complicates things. Whereas with the mode 2 that we have here, we can put the handlers and the interrupt vector table into the common shared RAM area, and that way we don't need to worry about what bank the machine is in whenever an interrupt is thrown. So that greatly simplifies the operation of the system going forward. We don't get this kind of convoluted issue of trying to deal with bank switching, reading the bank first, making sure we end up backing the original bank once the interrupt completes. All that operates seamlessly and we don't have to worry about it. And this comes back to the fundamental way that we are designing the system, and a bit of thought early on can really make your life a lot easier further down the track when you come to putting together the operating system. We will look at that later in future videos. The book does explain this in a lot more detail. The book will be available as soon as the project's finished or shortly after, and I am writing it as the project is developing. The project is always, as ever with videos, a bit ahead of what you're seeing. Obviously the videos tend to lag behind the real world aspect of this project. It's not too far, but the book is a few months away yet, and as soon as it's released I will of course let everyone know. But as I say, it does include all the circuits and schematics and explanations as to how all this works, along with the source code. So hopefully you may find it interesting or of use if you want to build one of these. So next step, let's get this attached to the Z80 and see if it does what it's supposed to. Okay, I've got the PS2 and the interrupt control circuits connected to our computer, so that's the Z80 card and the video card. I've got the PS2 keyboard plugged in, and I've got it connected up in such a way that it should work. I've got the output of the buffers connected to the data bus of the Z80. I've got the in-out request line connected, I've got the M1 line connected, I've got the interrupt line now going through to the Z80 board. I've disconnected the jumper I had that was connecting the interrupt line to V+ to stop the interrupts being kicked off all the time. And the actual PS2 port, I'm using an in-out port 1 to access the data. The reason for doing that at the moment is it's accessible from any bank, so it doesn't matter which bank the computer is in, and that's one thing to bear in mind. This is a multi-bank machine. It's not just a simple single bank design, so it is a fully fledged multi-bank memory mapped device. So you'll also recall that we had in the memory map circuits of the Z80 I'd included some in-out mapping and some in-out control. So we can actually access this now using a simple in command, and in this case an in of any port will access it. It will of course need to be mapped to a single port. We do already have some port decoding, so I can, if I want, use a specific port, but for now we're just using any port. I'm actually using a command of in on port 1, but it, as I say, would respond to any port within the memory map. So this is now connected, but if we power this up, it of course won't work. What we need now is to write some code to initialize our Z80 interrupt system, and then also a handler for the in-out port. Now I have had some suggestions over the last few videos that I could replace this with an adapter. It would save me having to write the code to convert that within the Z80, and well, yes, I could do that, but it would make this entire project completely pointless. The entire point of this project is not really to show how to build this particular machine. I'm trying to demonstrate the process we go through to design a machine like this. And if I start just introducing things to avoid having to do any of this, then the project becomes pointless. So thanks for the suggestions, but the point of the project is to show how to go about doing this the hard way, not how to just drop in an alternative. Now I appreciate that a PS2 keyboard could be deemed to be a more modern device, but they have been around since the mid-1980s, so they are vintage. You could even, as one suggested, replace this with an AT keyboard, an IBM AT keyboard. The protocol that this uses, or at least the character set that we're using, is compatible with the original IBM AT keyboard. But like I said, the reason I've selected the PS2 is because it should make this accessible to other people. So what I need to do now is go away, write some code. It will start getting a bit more complex because we're now starting to get to the point where we have to generate what amounts to the boot ROM. It won't be, of course, the full boot ROM, but we do need to start putting in place the general framework for it. So I'll get that done, we'll come back, and hopefully we can get this working. Okay, I've created a ROM which hopefully will allow us to at least get characters out of the PS2 keyboard using the interrupt mechanism. And just to quickly go through the code, I won't go through this in too much detail. If you want me to go through the code in more detail, then please leave a comment, but for now I'll skip through this fairly quickly. But just bear in mind, the purpose of this project is to show the overall process, not necessarily the detail, but I'm quite happy to show this in detail if that's what you want. So the code starts off, and by the way, I'm now using, of course, a compiler. I can't really start doing code like this the long-winded way I was just calculating the addresses in my head before, but now I need to start actually compiling more complex programs. So it's a bit more formal in the way it's laid out, just because this is now going to form the basis for our boot ROM. So what I've got is some equates, just so these will probably change, but by putting them into equates I can just change them in this part of the code rather than having to search through and probably miss some. So this is based on our memory map, and the main points we've got here are the RAM top. That takes us up to the bottom of the it's where the video starts, memory starts, less the interrupt table, and the interrupt table is just 16 bytes, but it sits between the top, what we deem to be the top of the RAM, and the start of the video memory. And then we've got the stack, which sits below that, and it will of course grow downwards. I haven't decided how big to make the stack yet. For now I've got obviously plenty of memory space, so I can make it almost as big as I want. We've got the video RAM start address, we've got the non-volatile start address, we've got the ASCII table. Someone suggested it was difficult to write code to convert between PS2 and ASCII, but it's actually extremely simple. You just really need a lookup table and then keep track of which particular packet you've received, whether it's a key down, key up, or the special code packet. Now at the moment in this code we are going to accept all the packets without interpreting them. This is really to test the interrupt controller. It's not to really debug the code, and I want to be able to see every single byte, if you like, that comes in through our system to make sure that we're capturing them all reliably. We've then just got a bit of dummy text here, so I can put this in as part of the overall structure that we'll come back to a later date. We've then got the start of the code, and the first thing we really do is to set our interrupt mode. Remember, we're going to use interrupt mode 2. We load the I register to point to the most significant part of the address of the vector table. In this case it's F7, so that's what we load into the I register. We initialize the stack to the address that we identified, and then we load the address of our keyboard handler into the interrupt table. Remember, the interrupt table is just a series of pointers to the handlers, and we need to tell the Z80 where to jump in the event that our interrupt is successful. The next thing we do is a quick loop to clear the video RAM. If you remember, when we boot up the machine, the video RAM is just full of garbage, so we'll clear that out so we can see more clearly what's going on. Very short bit of code, it's only about 8 lines, so it's might as well put it in. It will make our lives a bit easier. We then need to initialize a few variables. Now, one of the things I want to test with this version of the code, because it is quite important at this point to do this, is that the overall structure of our machine is working. So this code, if it runs, will test the access to the ROM, it will test access to the video RAM, and because we have a variable here which is in the main RAM, the DRAM, it will also test that, and it will test that it can all work together seamlessly without causing problems. This is just a pointer we're saving in RAM. Because we're accessing the video RAM in an interrupt, we can't really store or keep the pointer to it in a register. That's a recipe for disaster. So we store it in a RAM location that we can read and update and save to as we call the interrupt handler each time. We've then got a lookup table which is for the conversion of the PS2 code into ASCII, and by doing that it means we only need a few bytes for the actual code. It becomes very straightforward. It also means we can support multiple character sets if we want to. We then get to the actual keyboard interrupt handler itself. This is fairly simple at the moment. It will need to deal with the shift characters, but again, that's just really keeping track of the state of the keyboard. There are two sections to the lookup table, one for lowercase, one for uppercase, and some of the characters we can actually replace, which we'll do in this. It's a very short piece of code. In total it will be about 35 instructions by the time we've finished it. But for now, as I say, all I'm doing is accepting the incoming PS2 character, in theory at least, and then converting that into ASCII, and then we will be displaying that in the video and on the display. We'll use a pointer to the video, increment that each time we output a character, and that will cause the characters to increment across the screen, otherwise it'll all be in the same location. And then we save that pointer into the main memory and then load it and save it each time we come into the interrupt. And then we re-enable interrupts, and then we return, and that's the entire interrupt handler. You can see it's just a few lines at the moment. It will be bigger by the time we get handling in for the shift, etc., but for now this is just what we want. So in theory what should happen is each time we press a key, if everything is right and if the hardware is working, a lot of ifs there, we should jump into this handler, and it should then output 3 characters for each key press that we make. one for the key down, one for the first character of the key up, and one for the second character of the key up. And so without any more delay, we'll get this powered up and see what it actually does. But I'll move the camera so you can see the display. There'll be nothing to see in the hardware. I've disconnected the LEDs, don't want those loading up the data bus. So I'll point the camera, I'll put it so you can see the keyboard as well to start with, and then I'll move it across so you can see the display a bit more closely. Oh, and I'll fit the ROM as well. So I'll dim the light, we'll turn the Z80 on. Again, I'll hold down the reset key, and we should initially see garbage on the screen, but at least then we'll know the monitor is actually on, because what the code does, as you saw, is it clears the video RAM. So I need to make sure it's actually working, because if I got something wrong here, it could stop the machine from running. So I just want to make sure the video is running. So I'll hold down the reset, we'll power this up, and within a few seconds we should see a screen full of garbage. And we do, so that's a good sign. It means we haven't done too much damage to the machine. I'll release the reset key and it should fairly quickly clear that display, which it does. And so I'll press a key on the keyboard. Fingers crossed, we should see several characters appear on the screen at this point each time I press a key. So as you can see, or hopefully you can see, we're getting 3 characters. That's exactly what we should get. One for key down, one for the special character of the key up, and then one for the repeat code for the key up. So I'll press another key, and again, so that's working. Okay, now at the moment we're not getting the proper ASCII characters, and that's because the character ROM I've got fitted has the ASCII characters in the wrong order for what we want. That was for an earlier test. If you remember when we were testing the video before, it was starting off with uppercase characters, so it's going A, B, C, D, etc. And that's because I had those characters starting at address 0 of the ROM, which is obviously wrong. Uppercase A, for example, should be offset at 41 hex times 8, or 8 bytes per character, of course. But at the moment it starts off at 0, so we're getting just nonsense characters on the display. But even so, I'll just move the camera so you can have a closer look, and you'll see that we are at least getting characters coming through when a key is pressed. Okay, so you can see the monitor. I'll start pressing a few keys. Like I said, the characters coming through will be garbage. Incidentally, you can also now see the artifacts back on the screen. That's because I've disabled the blanking for those. If you remember in the previous video I said I'd put in some blanking. I'll just remove that. There were too many jumpers flying everywhere, so at the moment it's not enabled, so you will see the artifacts, but at least it goes to prove that that circuit was working. So press a few more keys. You can see that not only does it work, but it correctly wraps around when it gets to the end of each line. Okay, so that's a very good sign. It means we're getting what we expect to. I'll just move the camera back. So we're getting the characters we expect. It's responding nice and quickly. You can see it's not crashing or doing anything untoward. We should be able to clear the screen by pressing reset, which we can, and then it should be off again, which it is. So it appears our system's working. It looks like the PS2 interface is working, the interrupt controller is working, the interrupts seem to be doing what they should, and the system as a whole seems to be able to work the way it's intended. It can obviously access the main RAM, that's where the pointer is stored for the position on the screen, and that's working the way it should, and everything else seems to be doing exactly what it's supposed to. The next thing is to finish writing the handler for the interrupt so we can properly process the incoming keys and replace the character ROM with the correct one so that it's got ASCII characters in the correct order. But again, big step forwards. The system now seems to be doing what we expect it to, and we can start to interact with it.